Hey everyone! In this video, I just wanted to clarify the bidirectionality and leading versus lagging strand, which tends to confuse students many times during this unit. So what you have here is a single strand of DNA. So helicase has already broken the bonds between the nitrogenous bases, and the single-stranded binding proteins are helping to keep the strands separate. So we've already the mechanism has already identified the origin of replication, and what I'm going to do is I'm going to designate this phosphodiester bond here, shown in red. This is where my origin of replication is. Or rather, this is going to be kind of like my imaginary dividing line for where the origin of replication would be. And I abbreviate OOR, origin of replication. So remember that DNA replication is bidirectional, meaning that it's going to occur in this direction as well as this direction, away from the origin of replication towards each replicating fork. So take a look at, from this point here, the first carbon we encounter is carbon number 5. So in this direction, we go 5, 3, 5, 3, 5, 3. That means from the origin of replication going this way, the DNA strand is 5, 2, 3. Now keep in mind, DNA replication is going to occur bidirectionally, which means that we are also going to replicate going this way as well. Now from this point right here, the first carbon we encounter moving this way is that third carbon. So it's 3, 5, 3, 5, 3, 5 over and over again. So from the origin of replication going the opposite direction, the DNA strand will also be read in the opposite direction relative to this strand here. Now, Primase is going to lay down a primer so that DNA polymerase 3 can come in and begin adding nucleotides to this new strand. But one of the things that tends to confuse students is, well, how can I tell the difference between the leading strand and the lagging strand? And one of the things that I tell students to help them remember is that you always want to identify which new strand would be in the 5 to 3 direction. Once you've identified which new strand is going to be in the 5 to 3 direction, that is your leading strand. So the new strand being made, the one that's in 5 to 3, that is going to be your leading strand. So let's do a real quick sketch before I add the actual nucleotides of what these two complementary strands would be. So this strand over here, since the parent strand is 5 to 3, that means the new strand being made will be in 3 to 5. Then for this strand over here going this way, from the origin of replication, the new strand being made this way would be 5 to 3. Remember that DNA strands are anti-parallel. They're upside down compared to each other. So now that I know what the new strand is going to be, what I do is I look to see what that last available carbon is. So since this is going to be the OH group on carbon number 5, this over here is not the leading strand. In order for the leading strand, we look for which strand has, on the new strand being made, will have a free 3' carbon. That's this one over here. That makes this strand over here, the new one being made, is the leading strand. So this is the leading parent. So now that I've identified this as my leading strand, because it's got that free 3' carbon at the end, when Primase comes in to lay a primer, there's only going to need to be one primer on this side. And so a primer will get laid down, and then DNA polymerase 3 can begin adding to these nitrogenous bases. Eventually, DNA polymerase 1 will come in and replace the primer with actual DNA nucleotides. Once the single-strand binding proteins are removed from the parent strand, then the two DNA strands are going to come together. This is the old DNA, the parent copy that was read. This is the new parent copy that was made. And then there will be hydrogen bonds that are going to form right here. Now with the leading strand, which ends in that free 3' carbon, it'll always end in that 3'. The primer is only needed once, and the DNA will be copied continuously, meaning that DNA polymerase 3 can just keep adding until it reaches the very end. The other side, which is known as the lagging strand, has to be made different, because at the end of the lagging strand, it's not a free 3' carbon, it's a 5' carbon. So overall, the lagging strand will be made 3 to 5, but each individual segment, known as an Okazaki fragment, will be made in the opposite direction. So overall, we're going to be going from 3 to 5, but each Okazaki fragment will be made from 5 to 3. So Primase will lay down a primer further upstream from the DNA itself, from where we're going to be adding. And then what that does is it provides this 3' carbon here so that we could add nucleotides in this direction. Once DNA polymerase 3 has added the new nucleotides, this segment from the primer to the last nucleotide is known as an Okazaki fragment. So this nucleotide that's highlighted in yellow is the RNA primer, which is going to get replaced with actual DNA. And when that happens, you'll notice that there's a gap here, and there will also be a gap not shown here on the other side. So once that happens, once we replace DNA polymerase 1, replaces the RNA primer with an actual DNA nucleotide, all of these are going to have to get joined together through that dehydration synthesis, forming that phosphodiester bond, and that enzyme that does it is known as ligase. So the lagging strand, because it's made in those Okazaki stretches, is known as discontinuous replication. But please don't let the name confuse you. Discontinuous versus continuous, lagging versus leading, they will occur at the same rate. So one of them is not slower than the other.